Welcome to the Differential Equations course. This will be the first of a number of videos that we'll have for the course. There will be one for each lecture that you will watch prior to coming to class. It will discuss the basics of the theory and the techniques and work an example problem or two, sometimes more. Sometimes there will be more than one video for a particular lecture if just one video would be too long. So let's start out talking about differential equations before we actually get down to solving them. And so what is a differential equation? Well, let's just give a simple definition first. A differential equation is an equation involving derivatives. And so it's easy to come up with a very basic differential equation. dy dx equals x would be a very simple differential equation. And that turns out to be a simple enough differential equation that we can easily solve it. If we multiply both sides of this differential equation through by dx, we get dy equals x dx, and then we are able to integrate both sides of this differential equation because we only have one variable on each side of the differential equation. And when we integrate it, on the left side we get just y, the antiderivative of dy is dy, and we integrate x, we get x squared over 2 plus c, and so we've actually found a solution to this differential equation that easily. This differential equation is part of a general class of differential equations that we're going to study in this first section, 2.2, which is called separable differential equations. So a separable differential equation, I'll use the abbreviation DE for differential equation, is one where we can do this, where we can separate the variables, and so there's only one variable on each side of the equation, and then we're able to solve it just by integrating both sides of the differential equation. If all differential equations were separable, or such that we could put all the variables on one side, then we wouldn't even need the differential equations course. But it turns out that not so many are separable, and we need to learn a variety of techniques for solving them. And this would only apply to what we call a first-order differential equation. So let's define some terms here. So a first-order DE is one that only has first derivatives in it, and that's where we're going to spend the first several weeks of the course. And we want to talk about a linear differential equation. That's going to be one where all of the derivatives and variables are only to the first power, so it's line-like in that sense. So let's characterize that. So a linear first-order differential equation would have general form that looks just like this, and that type of differential equation, first-order differential equation, is the type that we'll solve in the second section of the chapter with our second lecture. So let's go back to separable differential equations and look at 3 or 4 examples of them on the next starting on the next blackboard. So this first example we have here, which is taken from the exercise set, an even exercise in the first exercise set, is not separable. Sine x plus sine of the quantity x plus y cannot be separated out, and it's not only not separable, but it's not linear either. The sine is not a linear function, and the fact that we can't separate out the variables x and y and put them on opposite sides of the equation is because the sine function doesn't allow us to do that separation. So let's look at a second example of a differential equation and see if it is separable. So let's take this differential equation. dy dx equals 1 over xy cubed. So this one, if we just do some pretty simple algebra, we see that it can be rewritten as what y cubed dy equals dx over x. And so it is separable, and because it is separable, after we separate the variables, we can just integrate both sides. When we integrate both sides of this differential equation, which is easy to do in this case, we get what y to the fourth over 4 equals integral of dx over x, which is ln absolute value of x plus c. And so let's box that in as our answer. We put a plus c when we write the solution on just the right hand side. We would actually get a plus c on the left side and a plus c on the right side, but we combine that together to 1 plus c on one side. And if we take this differential equation and solve it for y, we get what? We get y to the fourth equals 4 ln absolute value of x plus 4c. The convention, though, is to not write any constants times numbers, and so we just rewrite that as a new constant c. These two constants c in on this line and on this line are not the same constant, but the convention is to just ignore that distinction and just rewrite with a new constant c. And then we can solve this for y and get that our solution is ln absolute value of x plus the constant c, and notice that the constant c is bound up inside the square root. This form of a solution, when we are able to obtain it, the solved for y form of the solution is called an explicit solution. We will not always be able to get an explicit solution because when we get our solution in the two variables, typically x and y, we're not able always to solve for y. So let's go to a third example now. So here again, it's pretty easy to see that this is a separable differential equation. We divide both sides by 1 plus y squared, and we multiply both sides by dx, and we've separated the variables, and we are able to then integrate both sides. This would be a good time to review some basic types of integrals, because when we solve first order differential equations, we often have to do an integration step. And so let's, before we finish, let's come back to this one and after we've discussed all the basic types of integrals from Calculus 2 that you need to, will need to know to solve differential equations, and the types that I'll expect you to know when we take the exam. So of course we'll want to be using, or we will need to use the power rule for integrals frequently. That is, of course, x to the n plus 1 plus n plus 1 as long as n is not equal to minus 1. The special case when n equals minus 1 is this, which we just did in one of the previous problems, ln absolute x plus c. Let's generalize this a little bit to dx over ax plus b, which we'll need fairly often. Then we're going to let u equal ax plus b, and du equals a dx, or du over a equals dx. This is something that we will frequently need to do, this type of a substitution right here. So we get what du over u with a 1 over a out front, and we get what 1 over a ln absolute value of u plus c, or back in the original variable 1 over a ln absolute value of ax plus b plus c. So the occurrence, of the ax plus b in the denominator as opposed to just x made just one small difference between this solution here and this solution here, and that was the 1 over a out front. So this integral form is going to be the one that we're going to want to remember. Dx over ax plus b is 1 over a ln of absolute value ax plus b plus c. So let's go to a type 3 now. So this is one of several where we need to look at what happens when instead of it being just the more familiar type, such as e to the x, it's e to the ax, so we convert it using the substitution technique to e to the u du with a 1 over a out front, and so it integrates to what? 1 over a e to the ax plus c. And what are the other ones of this type? Well, we will often encounter cosine ax dx, so that would be what? Sine of ax divided by a plus c, and its companion integral sine of ax dx, let's actually make it sine of bx dx, would equal what? Minus cosine of bx divided by b plus c. So let's now go to the type that we are encountering in the problem that where we left off, the separable problem where we left off. This you, I hope, recall, or should recall, is 1 over a tangent inverse of x over a, an integral form that you probably derived in Calculus 2. And let's look at two other integral types that you probably encountered in Calculus 2. If we rewrite that as 1/2 1 plus cosine of 2x dx using one of the trig identities, then we get this. When we solve it, we get what? 1/2. We integrate the 1 to get x. We integrate the cosine 2x to get sine of 2x over 2 plus c. And then sine squared x would use this trig identity, 1 minus cosine 2x dx, almost the same identity as the one that we just used here. And when we integrate that, we get what? 1/2 x minus sine 2x over 2 plus c. Okay, so let's continue on the next blackboard. So some other trig integrals that we need to be able to do. So you remember that the derivative of tangent is secant squared, so the integral of secant squared is tangent x plus c. Actually, let's generalize that and make it tangent of bx over b plus c, with this here being secant squared of bx. And then another one that you have, I believe, encountered before, so secant bx, tangent bx, secant tangent is the derivative of secant, and so this would be then what? Secant bx over b plus c. And then look at a couple of trig functions where they're not so straightforward. The antiderivative of tangent x, or tangent bx, dx would be, that's the one where we had to write it as sine x or sine bx over cosine bx. We let u equal cosine bx, and so minus du is sine bx dx. It'd be an over b here, so this then turns into minus 1 over b du over u, which gives us minus 1 over b ln of u, but u is cosine x, so it's minus ln minus 1 over b ln cosine bx plus c. And if we want, we could move the minus sign up and make it this form, which is the more common form for this, which would be minus ln of secant x, right? Because if we move the power minus 1 up, that puts a minus 1 power here, and so we get minus ln secant x over b plus c as the antiderivative of this. And then one more trig integral that's not so common, and that would be integral of secant bx dx, which we have to rewrite as secant bx times secant bx plus tangent bx dx. So we're multiplying and dividing the numerator and the denominator by secant bx plus tangent bx. That makes the top, well, actually let's put the bottom as u, and the top is then just du or du over b, so we get 1 over b du over u, which gives us 1 over b ln absolute value secant bx plus tangent bx d plus c. Now the final two integral types that we're going to do are ones that we will not frequently encounter on exams, but every once in a while, and so they are one involving integration by parts and another involving the partial fractions technique. So let's take a look at an integration by parts type problem. The only type we will need to look at is when we have a polynomial function times an exponential or a trig function. In that case, you may recall that we always set u equal to the polynomial part and dv equal to the exponential or trig part. So an example of an integral of that type would be, let's say, x cosine x dx, then u would be x and dv would be cosine x dx, and with that selection we can calculate the necessary, right? We split this up as the it turns into by the parts formula uv minus the integral of v du. So we need du, which is dx, and we need v, which is obtained by integrating dv, which is what, sine x. And so when we split it up into the uv minus integral v du form, we get what u is x, v is sine x, and then the objective here is to get this integral v du to be one that we can do, and that gives us what, sine x dx, which is an integral we can do. Why were we not able to do this integral? Well, obviously we know how to integrate x, and we know how to integrate cosine x, but we don't know how to integrate the product of x and cosine x. because there's no product rule for integrals, the parts formula is actually as close as we get to the product rule for integrals. Certain types of products can be rewritten as a new integral. So finishing this up, we have what x sine x, and the antiderivative of sine x is minus cosine x, so it's minus cosine x, which is plus cosine x, and plus c, and then we have the answer here. And then in this last example, let's look at the partial fractions technique applied to a simple example. Let's say this dx over 1 minus x squared partial fractions. We're only going to look in this course at the type where we have linear factors in the denominator as a partial fractions type that we would encounter. And so we're going to rewrite this integrand 1 over 1 minus x squared as an a over 1 plus x and a b over 1 minus x, where we are calculating the a and the b. We're multiplying both sides through to clear out the denominator by 1 minus x squared, and when we do that, we get on the left side 1, and on the right side we get a times 1 minus x plus b times 1 plus x, and that is solved by what we call the zero out technique. If we let x equal 1, then the left side of the equation is 1. This factor right here is zeroed out, so 1 equals 0 plus b times 1 plus 1, right, because we let x equal 1, and so that is 2b equals 1, or b equals 1 half. And then if we, in the same equation, 1 equals a times 1 plus x plus b times 1 minus x, the other value of x that we want to choose is x equals minus 1. That zeroes out. That zeroes out this factor and gives us the left side is still 1. A times 1 minus 1, 2a equals 1, or a equals 1 half. And so we know this is 1 half and this is 1 half, and so our original integral dx over 1 minus x squared can be rewritten as 1 half dx over 1 minus x plus 1 half dx over 1 plus x. Let's rewrite that just a little bit differently as 1 half dx over minus x plus 1 half. This one we're just going to change the order, and you recall that we had this integral form. Let's see if we can get back to it right here. Dx over ax plus b integrated to 1 over a ln of ax plus b. The important thing that we want to note here is the 1 over a. So if we go back to where we were, the a right here is minus 1, and the a right here is 1, and so when we integrate, it's 1 half 1 over a ln absolute ax plus b. I'm going to write it back in this form, and then 1 half, the 1 over a is just 1, ln of absolute x plus 1 plus c. Combine that into a single logarithm, and so it's this logarithm minus this logarithm with a 1 half out front, and when its logarithms are subtracted, right, ln of m minus ln of n is ln of m over n, and so that gives us what, 1 half ln of the absolute 1 plus x divided by absolute 1 minus x plus c. And so this is the last type of integral that we will look at. So let's go back where we were, looking at a integral that we are doing by the, or I'm sorry, a differential equation that we are doing by the separation technique, because solving as a separable differential equation, separating the variables. So this left-hand side is one of the forms that we talked about. It's tangent inverse, it's actually 1 over a, 1 over 1, tangent inverse of y over a. A is again 1 plus c. We integrate this and we get what, x cubed plus c. Let's rewrite that and note that we can solve it for y. So it is tangent inverse of y equals x cubed plus c. If we take the tangent of both sides of this to, remember, I'll write this up in a second. So it's tangent of this side equals tangent of this side. And recall that when we have a function composed with its inverse, that just gives us back to the input variable. So the input variable on the left-hand side, tan of tan inverse, is just y, and then we get what, y equals tangent of x cubed plus c. An explicit solution is obtainable in the variable x. Oh, sorry, in the variable y. It would also be obtainable in the variable x. So one final problem that we'll look at. So here we want to get all of the occurrences of the variable x on one side and of y on the other side. It's not so obvious how to do that. First, let's multiply this out. So we've got x dx plus, actually let's not multiply it out. Let's factor an x out of this expression right here. So it's x times 1 plus y squared dx equals e to the x squared y dy. So here's a question that we haven't encountered before. On which side should the y variable be, and on which side should the x variable be? And we haven't asked this question before. And the answer is that y must be on this side because the dy must be in the numerator, and x must be on this side because the dx must be in the numerator. So in putting the y on this right-hand side, we're going to do what? Divide by 1 plus y squared, and in moving the x to the left-hand side, we're going to also need to divide by e to the x squared. And so when we do that, what do we get? We get x times, well, it's 1 over e to the x squared, but that's e to the minus x squared, is it not? So it's x e to the minus x squared dx equals y divided by 1 plus y squared dy. Now do you see which integration technique we need to use on each of these sides? It's actually the same technique on both the sides. And so what is that on this side, the left-hand side? Notice that this exponent minus x squared has as its derivative x, and so we're going to let u equal minus x squared, and so that gives what, minus 2x, or du equals minus 2x dx, or minus du over 2 equals x dx. So setting it up as a u du integral, x dx is minus du over 2, and e to the minus x squared is e to the u. And then on this right hand side we're going to use the same technique, right, because this is essentially our u, and this y dy is very close to our du. So if we let u equal 1 plus y squared, then du is 2y dy, or du over 2 is y dy, right? And so y dy is du over 2, and this bottom right here is just u. So when we set up that integral on the right hand side, we get 1/2 du over u. Okay, so let's box that in. So this is an easy integral to do. Minus 1/2 e to the u integrates to e to the u, and du over u integrates to ln absolute u plus c, and then just plug everything back into the original variables. So here on this left hand side, we let u equal minus x squared, and on the right hand side we had let u equal 1 plus y squared. And so so left side, it becomes, instead of e to the u, e to the minus x squared, and the ln of u becomes ln of 1 plus y squared plus c. This one is a lot of work to get in an explicit form, either solving for x or solving for y. And so let's just leave it in this form, neither solve for x nor y, and call that form, note that that form is called an implicit solution. We have not made it explicit by solving it for x. I want to wrap this up by solving one simple separable differential equation of a type that we haven't encountered yet. It's not a different type of separable equation, but it has an extra step in it, in that we are actually solving for the constant c when we were given initial conditions, or conditions for what y equals at some x value. We can solve for the constant. So here it's separated. It should be easy to see as dy over y equals sine theta d theta. We integrate both sides, and when we integrate both sides, we get ln of absolute y equals minus cosine of theta plus c, and then we plug in the initial condition. This is the value for theta, and that is the outcome value for y. So ln of absolute minus 3 equals minus cosine of pi plus c. Cosine of pi is minus 1, and so this becomes what, ln of 3 equals minus 1, which is 1 plus c. So c equals ln of 3 minus 1, and so our solution to the differential equation in implicit form is ln y equals minus cosine of theta plus ln 3 minus 1, and we can combine our logarithms together to get this. Ln of y minus ln of 3 equals minus cosine of theta plus 1, multiply both sides by a negative. Ln of 3 over ln of y equals cosine of theta plus 1. So this left-hand side becomes ln of 3 over y equals cosine of theta plus 1. And then let's actually get its explicit form. So we can remove the y on the left-hand side by making both sides powers of e. Left-hand side then becomes, right, since e and ln are inverse functions of each other, it just becomes 3 over y equals e to the cosine theta plus 1, which is the same as e to the 1 times e cosine theta. And what can we do next? Then we can take reciprocals of both sides, so we get y over 3 equals 1 over e to the cosine theta, and that's the same as what y over 3 equals 1 over e to the cosine theta, because right, 1 over a times b is 1 over a times 1 over b, and 1 over e is e to the minus 1, and this is e to the minus cosine theta, and then multiply by 3, and we get what, 3 over e to the minus cosine theta. And so we have solved this differential equation and put it in explicit form, and the constant whose solution was what? That c equaled ln 3 minus 1 is bound up in the final solution in a way that it's kind of hard to see. So we don't need to break it out any further than that. So the point of this final example was that in some cases, in cases when we have these initial conditions here, actually this is called a boundary condition. It's an initial condition when this input value is a 0, when the input value is other than 0, it's called a boundary condition. But when we have boundary conditions, we can solve for that constant c, and then when we write the explicit form, there's no constants, or the explicit solution, there's no constants left in it. So this is the end of this video on section 1 in the class. We're going to practice a number of problems in this section to get familiar with the technique of separating the variables out, as well as the integration techniques that are probably a little rusty from Calculus 2. So this concludes this first video on the course.